Hi, my name is Mahita Penmetsa from NCSSM Online, and for my M1 research, I looked at analyzing the difference in error of optimal and suboptimal control methods. I worked with another NCSSM student, Alyssa, alongside my mentor, a graduate student at NC State University. So just to start off, to define a few terms, my research is based on control theory, which is the study of changing the behaviors of any dynamic system, whether it is chemical or mechanical, by using inputs or changing the controls to, in the end, get the output you want. For example, in a chemical system, you could change the rates of reaction or the amounts of certain chemicals inputted to minimize unnecessary components. Optimal control is used to find the best way to control a system while minimizing the cost, and it is the most optimal and the baseline we're using to compare. Model Predictive Control, or MPC, is a control method that is also used to predict future behaviors by simplifying these processes to make runtime smaller. This is considered the suboptimal control method. To compare, optimal control is like planning a full trip in advance, while MPC is like adjusting your path as you go on, and MPC is widely used for chemical and other control systems. This research is very relevant because of its applications in many fields like chemical, mechanical engineering. We are not sure on how far this method is from the best possible control since there is research comparing these methods, but there's not as much research quantifying this error between them. So, my research question was, how far are common control methods like MPC from the best possible control, and how can we quantify that error? Our objective during this project is using convex optimization, also known as minimizing a control, to find the true optimal solution for a system. We will also use suboptimal MPC controllers with different settings on the same system to then compare the results by calculating these errors and seeing the difference. So first we had to choose a dynamic system to control. We worked on the Williams-Otto system. This is a six-state, nonlinear, and somewhat complex system, modeled with the inputs being called A and B, and the P as the product, and E as the neutral output. This is a chemical reaction, as shown with the equations, the three equations at the top, and we modeled the system with these differential equations. The x dot just means first-order differentials. We then used the Pyomo library and IPOP solver in Python to solve for the true optimal control to minimize total costs and balance product and energy usage. We then implement the MPC controllers to the same system with different prediction horizons, in this case making it 5 time steps. We then simulate the system under the MPC method. Afterwards, we will record and compare the performance between both of these control methods by calculating the error using the total squared difference between the system output and the set point over time, as shown with the equation at the bottom. And we would also graph the results over time to visualize any patterns or trends between both of them, between both of the methods. So here are my results, and they clearly show that MPC is not as accurate as optimal control over the total horizon. In this case, the blue line is optimal and the orange line is MPC, and you can clearly see for E, it's like pretty close, but for P, it's not close at all. It didn't work like at all for P, and there was almost 70% more error for MPC compared to optimal. So P was the product and E was the byproduct. So the total squared error for MPC was 16.6, and the total squared error for optimal was around 15, which clearly shows that there was more error with MPC. And yeah, so our conclusion shows that both optimal control and MPC effectively optimize the system, with optimal control performing much better. The total squared error for MPC was about 10.22% higher, showing that MPC is somewhat practical, but it has flaws that need to be accounted for when modeling the system. So, understanding the gap between these methods and optimal control helps engineers pick the correct balance between performance and simplicity in real-world systems like robots or vehicles. So in the future, we could test more complex systems which are difficult to model, but likely show the error between MPC and optimal control even more. We could figure out why the product had so much more error for MPC compared to the byproduct. And we could also explore the balance to make sure that MPC is more practical and applicable because it's so widely used, and we need to know more about this error. So here are my references, and I'd like to thank Jared Morris for mentoring me in Professor Wentao Tang's lab, NC State University, NCSSM Durham's mentorship program, the Burroughs Wellcome Fund, and the NCSSM Foundation. Thank you!